Now these are boundary conditions. In a typical electrostatics problem, you're given a source charge distribution ρ and want to find the electric field it produces E. Unless symmetry allows, Gauss's law is generally better to calculate potential first. It is an intermediate step. There are these fundamental quantities of electrostatics, ρ, E and V, which is our potential. All 6 formulas interacting, then we have this. Now, if we would begin with 2 experimental observations. 1, the principle of superposition, a broad general rule applying to all electromagnetic forces. 2, Coulomb's law, the fundamental law of electrostatics. From these, all these followed. Now, the electric field always undergoes a discontinuity when you cross a surface charge. In fact, it is a simple matter to find the amount by which the electric field changes at such a boundary. Now, suppose we have a wafer-thin Gaussian pillbox, like the example we were given before. Now, extending just barely out of the edge in each direction, Gauss's law states this. Now, these signs here stand for perpendicular, and if we had E like that, it would be parallel. Where of this area of the pillbox lid, if our surface charge varies from point to point of the surface and is curved, we pick it to be extremely small. Again, size contribute nothing to the flux in the limit as the thickness our epsilon goes to 0. So we are left with this by our boundary conditions. Now, where the normal component of the electric field is discontinuous by an amount here at any boundary. In particular, where there's no surface charge, our electric field perpendicular is continuous, as for instance at the surface of a uniformly charged sphere. Now, the tangential component of E, in contrast, is always continuous. For if we apply by Gauss's law here to the rectangular loop below, the ends give nothing as our epsilon goes to 0, and the sides give this as our parallel. So by our parallel boundary conditions are here. Now, parallel to the surface. The boundary condition of the electric field can be combined into a single formula here, where n is our unit vector as normal, n hat, and is perpendicular to the surface pointing from below to above. Now, the potential is continuous across the boundary, since here, again, our potential formula. Now, as the path length goes to 0, so does the integral v above v below. However, the gradient of v inherits the discontinuity in our electric field, since, again, by this relation, implies that, or this. Now, or in a more differential form of v with respect to n, taking our del, which equals this. Now, this denotes the normal derivative of v. And please do like and subscribe, there's lots more to come.